Those are just few, and these are, again, these are the features and the structural features that are going to use in comparing the programming languages, just for structural features. The second feature is the life cycle feature. The life cycle features in this group of criteria, it contains language features related to the kind of program behavior, management of object life cycle, and bindings. For life cycle features, it has an object life cycle, which is in the table 7, and binding, which is in table 8. Again, this object life cycle is unbinding are the features from life cycle features that are going to use again in comparing the uh, programming languages in terms just only for the life cycle features. And lastly, behavioral features. This is the last features that are going to compare between programming languages. So in the group of behavioral features, it contains features that are used to implement programs logic. For behavioral features, it has calls between objects, control structures, operational expressions, operators in expressions, and others operations. So these are the results for the comparison for supported features. So in the table shows a difference in the support of structural relationship between the Java and the Scala. So the features supported in both language or supported in either language are not included. As you can see that in the table, Java and the Scala only that are compared in this um, table for structural relationship. Again, the features supported in both languages or supported in either languages are not included. For the result for looking for equivalent keywords in this table matches equivalent phases of object lifecycle management in C++ and in Python. Unlike the previous table, which I presented earlier, features supported in both languages are included. These are the results. As you can see, majority of the features for the C++ and the Python, we have um, the yes answers. For studying spread of feature supports, support for piece-by-piece returns from a function, in the left column, which are the languages, and the right column is the supported column. As you can see, the Java, the C++, the Perl, and Ruby and Kotlin are the no supported languages, and Python, C#, the PHP, the JavaScript, the VB.NET are languages with yield, and Scala and Go languages may be emulated. Let's now interpret the comparison of comparison results. So only those traits that have a direct or almost direct analogous in the language under considerations are considered in the comparison tables previously presented. They don't explain how to build equal functionality in the language if there isn't a direct equivalent. To avoid misunderstanding, it is vital to define what the lack of support entails from a practical standpoint. This isn't to say that the language can't be used to address the not the problem. All of the language considered are Turing complete, which means so You can solve any problem in any of them, or we can solve it at all on a computer. So as a result, additional language features do not increase the number of tasks that can be solved. Instead, they can provide advantages such as programmers' convenience and software security. According to the researchers, the classification used in the study provides a general guidance on the consequences of the absence of the particular features. First, the absence of behavioral feature, which means that the required behavior should be implemented using other behavioral features. So obviously, it is always possible, but may require extra code, often but not always. This code may be uh, componentized into separate function and reused. So many such examples may be found in the popular libraries and frameworks. To add, absence of a structural feature related to a type means that the task should be solved using other data types. So it may lessen type safety. For example, if a program logic requires that the value of particular variables lies in a particular range, using an integer variable instead requires manual condition checks, so which can be accidentally omitted. Absences of structural features related to a relationship means that a programmer must bear with this relationship in mind without any support from the compiler. So it may require re-implementing some codes, so otherwise provided by the compiler, and lesson type safety because the relationship is not under the type control. Lastly, and the absences of a life cycle feature is a more difficult case since life cycle management and binding management are usually ensured by a compiler. So insufficiency of its facilities may require the programmer to write a lot of low-level codes. So inability to change a binding may require creating an object completely. At the same time, inability to prohibit changing a binding lessens the safety of program. Now we are down to the conclusions for the study. So the study addressed the problem of comparison of object-oriented programming languages in respect to the expressive power. Say, for example, their ability to express ideas in terms of which programmers think about their programs. Analysis of a few languages used for the description of programs and software systems such as UML, type theory, and the most popular design patterns. So allows the researchers to form a basis for such comparison. So this basis was validated and detailed in actual comparison of a number of object-oriented programming languages. The resulting comparison tables may be used for pairwise or group-wise comparison of programming language expressiveness. So determining language construct equivalent to the one of another language, so as well as studying the degree of support of a particular language level feature in different languages. And I think that's all. Thank you and keep safe always, everyone.